We got that far? Yes, no? And we'll go over there to the line and fire up and run it. I just got it running yesterday, therefore. So all y'all had DC, so y'all understand. Talk to them about FET. Talk about control systems. And we'll see that for sure when we get back and start looking at the line. We was looking at sensors. We talked about analog sensors. We got a couple of these on our manufacturing line. The Amatro line has both a digital pressure switch and it's got an analog pressure switch. There's an analog sensor on the Festo line. It's a potentiometer. We got two potentiometers, in fact, on the Amatro line. We got one we can use that's on the gantry train on the very end, on the right hand side. That's a big linear potentiometer. The one on the Festo line is actually measuring the height of the cylinders when they come up. So it's not linear, it's a linear too, I think. But you got potentiometers in DC, right? Talked about incremental encoders and absolute encoders. The Festo line doesn't have any encoders on it. The Amatro line's got an incremental encoder on the conveyor belt. We're talking about limit switches. We've got limit switches on both lines. We'll look at and see if we can see where they're at. Then we talked about magnetic reed switches. We got magnetic reed switches all over the place over there. We'll show you how to identify those. These guys sense magnetic field. Then we talked about the cylinders now, pneumatics. We talked about this being able to, since pneumatics is running at a fairly low pressure, then they can use aluminum or plastic on the cylinders. All ours are aluminum, and aluminum, what they can do is they can mount a magnet on the actual piston itself, and then we can put the magnetic sensors on the outside to pick up whether the position of the cylinders. Now all our cylinders, except for one, they fake it on the gantry train on the right hand side on the Amatro line, are two, what we call two position valves. So the cylinders, that's the only one we can stop in mid travel if we want to. All the other ones, they use two position valves, and all they can do is either fully extend or fully contract. So what our sensors are telling the program controllers that are fully extended or fully contract. So Hall effect does the same thing, but basically a Hall effect is an electronic sensor and a reed switch is an electromagnetic sensor. And we'll see, even though they use the same symbol, one of them is a 2-wire sensor and the other one's a 3-wire sensor. So when you look at the diagrams, when we start looking at symbols in today's class, we'll be able, even though the symbol for, they're both magnetic switches, the reed switch will only have 2 wires and the Hall effect will have 3. There's no signing anymore this semester. You're supposed to do the release form online. If you do the release form online, you're fine. So we're not going to have to do the daily signing things. We just found that out last week, though. Photoelectric, we looked at through the beam. Everybody okay? If you got anything you need to go back over, we looked at through the beam, we looked at retroreflective, and we looked at diffuse. Everybody okay on those? Both lines have these optical sensors all over. And then, of course, I think this is where we left off on the optical interrupters. The only one that uses them right now is the Amatro line. They use it on the gantry train. So we mentioned the gantry train. A gantry train, by the way, is one where it's up in the air. Capacitive inductive. I think we looked at these too. So we have two types of mounting, we have what we call a shielded and an unshielded. So an unshielded has a wider sensing range. Shielded is a narrow sensing range, but we can use these shielded ones. We can mount those flush. So we'll see several of these over there. We've got both types on both of our manufacturing line we're looking at. But a capacitive sensor can sense both solids and liquids, right? You understand that? And in this class, we don't need to know how it does it. We just need to know what they do. And then the inductive sensor senses metal. And like I said, you've ran over these all day long. That's what we use to sense when the cars are at the red light. So inductive sensors sense metals, and we can get them in both shielded and unshielded. So ultrasonics basically works like radar. So what we do on ultrasonics, we use these. We can use them to measure speed. They can be analog and actually measure distance for us. In fact, this is what they used on the tank farm down there in Pelham to actually measure the height of the gasoline. That's actually gasoline in there, by the way. It's not oil. Those are actually gas tanks down there. Or they can be digital. Ours is digital, the ones that we have. And we have two. It's set up, and I don't know if y'all can see it or not, but we'll look at them. It's what it's doing is it's measuring to see if the valve blocks are the right height. So one of the things we'll do toward the end of the semester, we'll actually calibrate this sensor. So we'll let y'all act like you're going to remove it and replace it like it was bad. And then when you replace it, you'll have to calibrate it. And of course, it sends out a pulse, and then it measures the amount of time that it takes to get up. But this guy here has what we call a span. So, oh yeah, you see what's going on? Yes, thank you. It's crazy.
Yeah, that's really hard to do, right? That's why I have to move up there.
Our ultrasonic sensor is measuring when it's too high or too low. So what I was telling you is that this is a digital ultrasonic sensor, and what we do is we set an upper limit and a lower limit. So we'll show y'all do that. Y'all have to do that toward the end of the term. So ultrasonic sensors can measure distance, movement, levels of solids and liquid, speed, and direction. So ultrasonic sensors. That's Matt. It's mad at us, man. Take her that off. Well, we could, but our lines didn't work. Pressure. We have pressure sensors on both lines. And we have different methods we can do that. Anybody that has a compressor at their house, come here with these guys. We're fixing to hear one in a minute. So there's a pressure sensor on this compressor there. And when it gets up to a certain pressure, it'll cut it off. And then, of course, when it gets down to a certain pressure, it'll turn it on. So it's got an upper lower limit also. Most compressors, those are preset. I think most of them will charge up to around 100 pounds, and then they'll discharge down to around 70 or something. So we have different types. It's not really important for us to know in this class. This is actually, I think, for the actual census class. We have diaphragm types, we have spring types, different. We do have an analog sensor, a pressure sensor on the Amtro line, but it's is not being used. The Amatro has a lot of sensors that we could program into the program controller. So right now, a lot of it's not being used. We are using the digital analog. We are doing the digital pressure sensor. What it's doing is we can create a vacuum to something we call a Ventura. Anybody who's got a pressure washer knows that. So you can put soap and stuff into it, and it'll automatically do what? Even though it's shooting it out that way, it'll automatically suck it down and add it to your stream. But basically, we send it to like this, and then when it goes through this narrow, it creates a vacuum. So we come over here. So both of our vacuum or suction cups on both of our lines use as a Ventura a vacuum generator. But it measures the pressure. It doesn't measure the vacuum, it measures the pressure. Because if you don't have the pressure, you can't have the vacuum. And the amount of pressure it takes would be proportional to the amount of vacuum it generates. RFID tags, all y'all ran through these, even though you don't know it. These are radio frequency identification tags. There's two types. We have what we call an active type, which basically has a power source. They'll have like a battery or stuff. And then we'll have a passive type, which basically works on induction. So everybody's had a little talks on induction. Y'all know how that works? Yes, no? We can show you. We got a transformer out here. So if I put a magnetic field into a wire, it's going to induce a voltage unit. So they power up off the sensor. They actually do that. They power up off the sensor. And so this is what they got. Like a lot of tags on Walmart, they have to take them off when you go out on certain things that cost a lot of money. They have the passive types as far as I know. So RFID tag reader is that blinking light back there that's setting us off line on to the left of the robot station. See the little green light flashing off them. And we're not using that in the PLC program either. But we have some of the blocks that we have, or the valve blocks that we have. They'll have black RFID tags on one side, and so you can see the ones that would work. It would pick those up, and I don't know what information is on there because we have never used that yet. But a lot of stores have them, especially with electronic equipment and stuff like that. And it's got some of them, they can actually blow a fuse in there. You ever see them where they swipe them across that thing? Well, what happens is it puts out enough energy on them, and it blows a little fuse in there, and it disables the electronic circuit. Temperature, we don't have any of these on our line, but these are important to know. We have what we call a thermistor. This is a solid state device. It actually changes its resistance. So this is usually what thermostats use that controls your HVAC system on your house. It usually has a little thermostat, a little thermistor in there. We have two types. We have NTCs and PTCs. The most of them I've seen is NTCs, which is negative temperature coefficient. And what that means is as the temperature goes up, its resistance goes down. So these guys vary their resistance with temperature. Very easy to use. The only problem we have is they're not linear. So if we looked at the curve of R in temperature, we'd find out it does this. So we don't use these over a wide range. So we'll come in here, and if we use it over this little range right here, it appears to be linear, right? You understand that? So this is why, your HVAC system, you don't operate your house over a big wide range of temperature. So the coldest we put ours down is like 66, at night, and during the day it's like 73 degrees. So that can use a thermistor because it's SWAT. We're over a very, very narrow range. Now they can compensate for the nonlinearity with a computer. So we do have some chips. We do have some like LM35s. LM, it's gonna take a little while, I'm doing this on another. What I need to do is, LM is very, very popular now, but infrared sensors, these guys are electronic circuits. You just don't have an infrared sensor that exists by itself. So RDT, you know, those guys do it without any electronics. Of course, we're gonna have to add something to it because we can't transmit resistance, right? You understand that? We can transmit current and we can transmit voltage. So that's the two things that most sensors use. They either use a voltage or they use a current. Most analog sensors run from 0 to 10 volts or 0 to 5 volts. The digital sensors are usually digital sensors are 0 and 24 volts. That's most of what we do. Well, let me get to the right place. Infrared, y'all probably ain't coming in the gate. The guy didn't even touch you, did he? What he did. And so that infrared sensors they're electronic sensors. They can't exist without having electronic circuits. Okay? Well, what's nice about it? In the old days, people, HVAC systems, if they wanted to measure the temperature coming out of the vent, they would have to have a ladder and they would have a thing that was a lot like a meat thermometer that you stick in the meat. And that final thing is stick it in the vent and they'll watch it. They didn't have time to respond. So now what do they do when they measure the temperature out of the vent? Yeah. Now the laser pointer, that's not the sensor. That's just the aim. So it's like these people have lasers on their guns. It's not, we don't kill with a laser, we kill with bullets, right? And that's all that's doing is that you have to have very precise alignment or aiming to measure those things. So most of your infrared sensors, except for the one the guy's got out front, because he's putting it like this, they'll have a laser on them, especially if you got a point. Solenoids and relays. I think, if we talk a little bit about these in this class, I'm doing another class, so I need to let you know. So when we put, I didn't hook up my camera. So when we put current through a conductor, it generates a magnetic field. And I don't have it in here. Oh, yeah, it is. Pause this. Sucks the plunger into the core. And we call these solenoids. Solenoids are all over the place. They're on washing machines. That's the devices down at the back of the washing machine that turns on the hot water and the cold water. So there's two solenoids down there. And then the plunger actually goes in and blocks the water. Ice makers, if you got ice makers, they usually have solenoids on them. If you ever gone to a place, they say buzz me in. And that's got a solenoid. They had tons of them up at UAB. And they was rolling me all around to get my thing. Now we can attach the plunger and we can attach or make it move an armature, and then the armature can open and close contacts, and these are relays. And what's nice about a relay is the contacts are completely isolated from whatever's running the coil, and we call them coils. So we could have AC on the contacts, we could have DC on the contacts, we could have a DC coil running AC circuits, we could have a low-powered relay controlling a high-powered device, like, the lights on your car. So if you ever went out under your hood and pop the hood up, you got a big black box on there, you pop that sucker over and it's probably got 15, 20 relays, along with fuses. It's got a lot of relays in there. So what that does, it allows you to turn on your lights with a little switch on your dash, you know, your lights are pulling 10, 15 amps, and you're doing it with a little switch on your dash or a button. Well, what you're doing is you're energizing that relay out there, right? It's got a pretty good size relay on your starter. In fact, it's called a starter solenoid, what it is, but it's actually a relay too, switching the current to your starter. So we use relays all the time. There's relays on both these manufacturing lines. The Amtro line uses some of the relays you'll see. The ones that's on the Festo line are very small. We call them peanut relays. They're very small relays. But the Festo line has actually got some reversers on there. It's pretty neat. We'll show you all that. By the way, most industrial relays have mechanical overrides on them. Be real careful about that. We'll show you all those too. In fact, that's one of the ways we do it. Sensor wiring, we have 2-wire sensors. We can have AC or DC 2-wire sensors. We can have 3-wire sensors, or we can have 4-wire sensors. Now, these are electronic sensors. And normally they only give you one output. Or they give you 2 outputs, but one of them is going to be a simulator normally closed and normally open. Normally we're going to use these things to run into a programmable logic controller. And then the programmable logic controller can make a decision, implement a program, which is a really good class to take, by the way. Somebody had PLCs? I think James does. Yeah.
All 3?
Yeah, all 3. Yeah, James does them. So one of them we do, we're adding I think I told you, we're adding the Allen Bradley certification to the. So this is electrical control. So anytime you see an electrical control, basically the sensors have one symbol, and you don't know what it is. You don't know if it's an optical sensor. You don't know if it's a solid state sensor. I mean, we know it's solid state because of the diamond shape. So this means it's a solid state sensor. And then the symbol they use is the symbol for a limit switch. Even though it might, so it's just, and the switch in there is usually not a mechanical switch, it's an electronic switch. So the way these things work is they actually, they're electronic, so they power up through the load. So when you take motor controls, you'll use a inductive sensor, and it's solid state. It only has 2 wires, but these lines are 120 volts. The sensor, to operate the sensor, takes to generate enough power to operate the sensor, it drops about 4 volts. But still, that still leaves you 116 volts over here to run the load. So they're actually powering through the load. These 2-wire solid state sensors. Most of ours are like this. So what we do is we have this, and then we have an output, and then if we have to power it up, it goes between the 2 power lines. And these would be 3-wire sensors. And the power is usually 1 and 3 on these sensors if they're numbered. And then the output is either 2 or 4. Actually, this guy right here should be 4. Should be 4. So what these work is what they have this. And then the normally open would be 4 and the normally closed, would be 2. No. The normally open would be 4, and the normally closed would be 2. So we can look at these over there, and we'll show you how they wire up. All our solid state sensors have to be powered. The only ones that are not powered is the reed switches.
Aren't they supposed to be color coded too?
Yeah, they are. This is the L1 side. This is brown, and this is blue. And then the normally open which is 4, is black. And then if we have a normally open, if we have a normally closed, it'll be white. Normally. And this is not always true, but it's usually true. It's not always sensitive. So a 4-wire sensor has a single pole double throw simulated contact. They're not actually contacts, they're electronic. So one thing you got to do over here is you got to know the motor control thing. So limit switches. We have limit switches. These are mechanical switches that it actually has to make contact with. So normally open. And what you do on these guys is you look at what gravity is going to do to it. So we got this dot if it's drawn right. So gravity is trying to open this, and it's open. So this must be a normally open. When I come over here and look at this, gravity's trying to close it. So this is a normally closed. The problem with limit switches is when you park your machine, what happens is sometimes it's going to sit on top of a limit switch. So the normal position of the machine, or the static position on the machine, and we've got these right now, is that sometimes in the normal position or the parked position of the machine, a normally open might be held closed, or a normally closed might be held open. So if you look at this one, gravity's trying to do what? Gravity's trying to open it, so it must be held closed. On this one, it's not drawn real well. Gravity's trying to close it, so it must be held open. So limit switches can fall into that situation. We got on the PLC, I fussed about this, they talk about symbols, and they've got a normally open, they got a manually operating push button, and they give the symbol for held closed. They said, this is a normally open push button, held closed. I said, okay, we got an operator over there doing what all day long? Holding them back. I said, there's no such thing as a momentary contact, manually operated switch that is held closed. So, but the symbols are in there. This is a foot switch. Y'all probably seen these. This is a foot switch. This is wrong. I don't know what that term is. It's either true or false, open or closed. Of course, we'll say true. Most of these are digital. They're either true or they're false. And all these are digital symbols. Nickel level switch, sensor switch, flow switch. So this is important when you're looking at a diagram. The symbols inside a PLC program are very simple, but anytime you connect something to a PLC, you're supposed to put the true symbol that's out there. Does that make sense? So usually electricians are wiring the PLC. Some of them actually programmers, and they've got, and so that means when you draw the symbols and look at things up to the PLCs, you use these guys here, or the IEC symbols that we're watching. So, selector switches, of course, these are not, I'm not have to know these on the timers. So I don't know, these blowout coils, I wish we had these. The problem with DC is AC does arc sometimes and it doesn't extinguish, but AC tries to be self-extinguishing. When we have an arc, y'all know why? Well, what happens with AC is it goes to 0 volts. In Alabama Power or TVA, it's 120 times a second. So at that 0 point, even though it's there a heartbeat, there's no current flow in the circuit. So AC has a tendency to be self-extinguishing. DC's not, because it's what? Yeah, it's all the time, right? You understand? So normally what we do is we run the load through what we call some blowout force. And what happens, it builds up a magnetic field. And this happens kind of like when you're in a swimming pool and you take your hands and you put them together and you try to open them real fast. What happens to water? It comes in between your hands real fast, right? Well, that's what blowout coils do. So they build a magnetic field, and then when you turn the power off, the magnetic field comes collapsing down and literally blows the coil out. We had a crane at U.S. Steel, 250 volt DC crane, and one of the arms on the blowout coil fell off. You know, when they turned it off, it just kept doing what? and the motor kept running. So it was, they couldn't turn the motor off unless they killed power on the train. So, but one of the blowout coil wipers that fell off. So you probably won't run into this much anymore because DC motors are slowly, they're not near as popular as they used to be. The biggest advantage we had on DC motors, and it still is we can precisely control. We can control the torque by playing with the field. If I increase the field, the motor slows down, but the motor develops more torque. We can increase the voltage on the rotor, and the motor runs faster. And we could do that with devices like solid state. We can do it with resistors. We had a 5-speed crane at U.S. Steel, and the way they changed speed was just switch the armor to a bunch of resistors, and it was inside a cage because they got pretty hot. So we can control that with resistors. AC motors are harder to control at speed. They want to run at a speed. Anybody know the formula? 120 times the frequency divided by the number of poles. So normally some motors are designed, some AC motors are designed to be controlled with voltage. Most AC motors are not. So if you lower the voltage, the motor slows down, don't create the torque, and it'll stall and burn up. If you try to increase the voltage, once it runs at speed, it'll burn up. So normally the way we control it is we can control it with frequency, but we can't control it with the frequency because of something called X of L. But once they figured out how to control AC motors and control them precisely using, I don't call them variable frequency drives, I call them variable speed drives. Because you just can't change the frequency, you have to change the frequency and the voltage to control these motors. Once they came out with those, these are starting to dominate the speed control industry also, because there's AC motors are just so much cheaper. So you can buy a DC drive and a DC motor, or you can buy an AC drive and an AC motor, and AC motors are very, very cheap per horsepower. So AC is once they came out and figured out how to control the voltage and the frequency, AC motors are dominating speed controllers. If you get into some old applications, you'll get into DC drives. Newer applications, it's probably going to be all AC motors because of the price of the motor. And also DC motors, you have to take care of. This is the DC motor that was running on we got our Festo line. We got it back in 2006, so it's been around a long time. And the motor that's running the conveyor went out on it. Well, the problem with DC motors is they have to have brushes, and most AC motors don't. They always do. So what finally happened? I know I'm not. The brushes finally wore out on the thing. So this is all the stuff in the brushes. And one of them is just flat one on it. So, of course, look at this. unit. In fact, I wasn't even screwed on it, it twist on there. So we had to buy the whole assembly. They have a burnishing tool, burnish the commutator. What's up to that? And we'll talk a little bit about motors. And you'll still run into DC motors, especially like in your car. So every motor in your car is a what? DC motor, yeah. So, you've got, still got a lot of DC motors out there, but usually in the industry you might still run into some, but they're predominantly AC. So you can see the brush just finally wore out on it. So this was all sealed up, and the gearbox is actually built onto the motor. So we had to order this. I forgot how much we paid for it. These are timers. So on delay timer, the arrow points toward it. Off delay timers, the arrow points away. So y'all know of any timers? Y'all running any timers? Huh? Timers in your house. You got any timers? Microwave. Yeah, probably the air conditioner, right? HVAC. Cars got a lot of them on there. Alarm system, they'll stay on so long, yeah. Yeah, mine does too. I don't like that. So I have a laptop computer. Motors is that they require a lot of starting current. But once they're up to speed, the current drops back. In fact, motors will have a code on there. They don't tell you what the starting current is, but there's a code on there and you can look it up on the chart and they'll tell you the multiplier. So if you look at the amp rating on a motor, that is not the start current, that is the run current. If you're running it, it's rated horsepower, it's rated voltage. Rule of thumb is start current, to get it started, is 6 to 8 times your full load current. So if you had a motor that required 10 amps to create its horsepower at its rated voltage, it would take about between 60 and 80 amps to do what? Get it started. So up here when they got their motors and they used fuses, and there's a lot of fuses still used in the industry, guys, because they're so cheap. So those are going to have to be rated to let the motor start. In fact, they're rated between 125 to 150% over what their maximum current is. And then you round up to the next standard value. So you multiply it by 1.25, and if it don't fall on a standard fuse, you don't round down, you always do what? Always round up. So the problem is, if it's going to let that motor start, if the motor stalls, those fuses will just sit there and your motor just flat burn up. So we need something that allows the motor to start, but if the motor stalls for a little while, it'll disconnect it. So this is what these overloads are. So these are overload sensors. So what we do is we'd have these overload sensors in each line. Like this, and then the motor would be down here. That's going to be off the screen. And what would happen is that if your motor stalls, these things would trip the actual relay. If I had this, and then there would be an overload contact in the control circuit, and that's called an overload, that would drop out the main control and kick the relay. So just about all your big motors are going to have overloads. Even small motors have overloads on them. A lot of them are internal. If we was over in the motor control lab, I could show you an internal load. So most of your overloads on your motors in your house are going to be internal. If they're sometimes they'll have a little reset button on them. They'll have a little reset button on them. where you can reset the overload, but most of the time they're thermal overloads. They'll use a bimetallic strip, and what happens is when they cool down, they'll automatically reset. So don't go out there and work on your air conditioner if your motor's not running and leave power on it, right? Because if that thing cools down, it'll skip back on, and we might be calling you nutty. So, we had this is a true story too. The symbols we're going to use are, so these are what we call, these are the symbols that I learned, and they're still out there. We're going to look at the IEC, the International Electromechanical Commission. These are the ones that we'll see most often used in our area now. And what we're going to do is that when we connect, so we got a program controller, and we'll look at this too. So what we do is we looked at what's required for a control system. And in the United States, eventually you're going to have to learn these, because we still have a lot of ANSI guys out there, and Allen Bradley and that kind of stuff. And this is the symbols that the most of the electricians over here know. But if you get into most of these German companies, they're going to use other symbols. So both of our manufacturing lines will use Siemens PLCs, which of course are predominant in Germany. Even though the Festo line uses Allen Bradley PLC, Festo is a German company. So the diagrams that we're going to use are going to be using the IEC system. And of course, why we're going them over here, because if you go to work for a company, a fully American company, and odds are they're going to use these symbols over here. And these are going to be the ones that's connected to the input of the PLC. There's very few symbols inside the programmable logic controller. Very few. So that answers your question, or I talk around it. So we'll show y'all the symbols that we're going to show y'all. So some of them are, even the symbol for a light bulb is different. So our symbol for a light bulb is 6 wires. These would be the power wires. But the IEC symbol for a light bulb is that. So it's a circle with an X on it. So what we're going to do is we're going to read our diagram. So we're going to be more concerned with the symbols that we're going to run into when we look at our diagram. That's a really good question. Which are these? So these are the IEC symbols, or ISO, International Standard Organization. These are the symbols that are used by our PLC code. So can y'all see these? I'll run these off and give them to you. So over here we use squares. So all the sensors, if you see a square, it's some type of sensor. Except for a limit switch. The limit switch still uses basically the same symbol that we use over here, which is the slanted line with a ramp on it. But they do use a different symbol for normally open and normally closed switch. So this is the two symbols. And no matter if it's a double break switch or this is the symbol they use. So double break, you'll run into a lot of double break switches in industry where they have a contact, and then they'll have a contact up here. And then this will be mounted on this, and then it'll be mounted on a spring. And this will be. Now, why they like those is it has 2 chances to break. So if one of your contacts gets stuck, then it's going to pull it up and make it come up with an angle, and we call these double break contacts. But we don't, even though the switch itself is a double break contact, or even the relay is a double break relay, we don't draw them like that. Okay. So on the left, this is, and these are electronic sensors, but they show you the symbol of a switch, and there's no switch inside there. It's just it's done electronically by transistors or FETs or whatever. So an inductive sensor, can y'all see we have this, and then we have it's solid black. So if we see that inside that, it means it's solid state. It's a 3-wire sensor, and we're using the normally open. So one, this is going to go to ground. This is going to connect directly to the plus 24 volt supply. And then the 3, this is going to be the minus. So this is the plus, I'm sorry, this is the minus. This is going to be blue. And then the normally open is going to be 4. This is going to be black. So this is a 3-wire sensor. And since we're only running on 24 volts, it has to be powered up off the power source. So this guy here will go directly to the plus. This right here will go directly to the minus, and this right here will go to our programmable logic controller. Ultrasonic sensor is the 3-wire sensor. So 1, 3, and 4. Everybody okay there? Photoelectric proximity sensors. All ours use the transmitter and receiver inside the same unit. I think this is best. Okay, guys, let's go ahead and take a 10-minute break. Now, everybody know where they're at in here. Y'all know where the restroom's at? Okay, anybody comes in late, it's a little symbol. Erase is not one of those. Untally stuff. Is this little guy right here. So that's going to be what identifies the sensor. So if you see this, looks like a resistor, but it's all solid black. This is going to be an inductive sensor. What does inductive sensor sense? Metals, good. If you see this guy right here, it's a symbol for a crystal, by the way. This is here, it's hard to see on these, but that's a ultrasonic sensor. Should be. This is mechatronics. There should be a. I thought I just said that. Okay, that's okay. So this is a photoelectric sensor where the transmitter and receiver are in both units. So we can't tell from it if it's diffused. We can't tell if it's through the vein. We can't tell if it's retroreflective. All we know is the transmitter and receivers in one unit. And we'll look at those, especially. There's only one of these on the Amatro line, but the Festo line uses all over the place. This little trough right here indicates it senses magnets. It's a magnetic field detector. Now, for some reason, Amatro, when they drew theirs, if you look at it, and this is black, they've only filled in half of it with black. We'll see the symbol right here. Now notice, this has the same symbol, but it's a magnetic reed switch. A magnetic reed switch is a 2-wire sensor, and then a Hall effect is a 3-wire sensor. Can y'all see the difference? So notice this has a 4. This only has a 1 and a 3, because the 3 goes through the load, it powers through the load. Are we okay? Yes? No? This is on the Festo line, but if you see this symbol, then can y'all see that? It's a symbol of a light emitting diode. Because this guy, notice the arrows on this guy points out. This one, so it's a photo transmitter. this one, the arrows are pointing in. So this guy senses light. So this is we call this guy a photodiode. And y'all know what this guy is. This is a symbol for a light emitting diode. It's supposed to be all referred to as LEDs. But this is a limit switch. So it comes over here and it says it's going to be normally open or normally closed. I don't know if they got any hell though. But it's got a circle, drops down, and then, well, these don't have, oh, by the way, this is motor control. This comes in, drops down, then you have the little slant, and then this is a symbol for a limit switch. These are electromechanical, right? And here, I forgot this one. So this symbol right here, if I see this on here, here's one right here. This is a capacitor. Now, why do we need to know this? Is that this is the wiring of the PLC, and this is the symbols. And notice this is the IC symbol that we're going to run into. And so this is part of troubleshooting. You know, this is what you need to know. We'll show you how to figure out where it's at on the PLC and that kind of stuff too. And you see, this is some of that. It's not all of them. This is some of the prints. And we'll go back on the line in a minute and show you all. So there's a limit switch. This right here is a pressure switch. It's got the little triangle in there. It's got a P on there. We have valves that we're going to learn about, of course. We call them directional control valves. So what we do is we control the direction of the flow of fluid, but we do it with so this is the one of the diagrams for the pneumatic circuit. So there's actually 3 circuits on this here, and then y'all know what an actuator is? A motor is an actuator, but an actuator doesn't have to be a motor. So a motor is a device that takes some type of pressure and converts it into motion. So on our cylinders, we call them cylinders, guys, because they still round, even though to us they look like they're squared. I think we looked at this one. We call this guy here a double acting cylinder. So we use pressure to not only extend it, we also use pneumatic pressure to retract it. This is the same symbol if you're in hydraulics, fluid, you know, that uses water, they use exactly the same thing. This indicates, there's that thing right there, so this indicates there's a magnet. That indicates there's a magnet on the piston. 1V1, so this is, we'll go back, let's see. Where's that at? I need to look for that. So what we do is A means it's an actuator. B means it's a sensor. So they tell us we got 2 sensors right here. 1V1, 1V2. So there's a sensor that senses when it's what? Retracted and extended. So we have 3 circuits here. You notice all of them start with a 1, so it depends on the actuator. So 1A, everything that controls, that has anything to do with controlling actuator 1A starts with a 1. Here's circuit number 2. Can you see everything inside here starts with a what? 2. Here's circuit number 3. everything in here starts with a what? A 3. In circuit number 4, everything starts with 4. And this is standard, which is pretty neat. So this is like a parallel circuit. So we got all these series parallel. So we got our power running down through a what we call a manifold. So all these valves rest on the same manifold. That's this. And so this right here, this guy right here is what we call a directional control valve. So this is a 2-position valve, and it's got 4 ports. Your odd port numbers are your pressure ports. So there's going to be so 1 is your pressure, and then 3 is your exhaust. And then your even numbers are your working ports. These are the actual ones that are actually controlled, that were shifted around. And the way these symbols are drawn, so this would be a 2-position 4-port valve. And we'll actually it's called a directional control valve. Did you ever see why it's got that name? So this actually controlling the direction of the fluid flow. This means it's got a spring return. And this is a symbol of a solenoid. There's an E in there somewhere. I know it's something wrong. So a solenoid, we know a solenoid does what? Creates linear motion. So what's happening here is the solenoid is actually causing the valve to shift. This symbol right here means it's got a manual override, which means what? We can shift it. It's got a little hole there. You can take a little tool and put it in there and you can shift it. You got to be very careful about manually overriding these directional control valves. This controls an actuator, right? We had a guy when I was working out at US Steel. He was up in number 8 blast furnace. It was a positive pressure blast furnace. So it had they would take they had a belt that would take all the material up to the top. They would open up a hopper door with a hydraulic. They'd close it, and then they'd open up the bottom one and let the material fall in. They was having problems with one of the valves. They went up there and they locked it out. They disconnected stuff, and he was up in there in that hopper, and they was going to force the thing, and they forced it, and the guy went down there and forced the wrong valve, and they didn't lock off the other valve, and the door come up and did what? I wasn't out there, but they said they brought him down in 2 pieces. See? So be real careful and know the consequences of forcing these things, manually overriding your automated system. Because all your safety is in the automation, not in the manual override. But we'll have to use them, and we know what we're going to do. So when we adjust the ultrasonic sensor that senses distance, we got to stop the dang carriage in the middle. Well, we're gonna jog it out there by doing what? By doing manual override. Well, we're gonna be right there. But if you imagine that thing was 50 foot long, and it cuts somebody in 2. So you got to be real careful when you manually override these things and make sure that everybody knows what you're doing. And it was, whose fault was it? Well, it was the guy that was in the hopper, because he should have did what? Lock out the other one. Yeah, locked and tagged the other one. Besides the one they were working on. So that's a manual override, which means I can shift this valve. Now what you got, but once I shift it, as soon as I de-energize the solenoid, by the way, M's are solenoids. So A is what? B is what? Some type of sensor, B is some type of valve. M is a solenoid. SELINO. There's an E in there somewhere, guys. So this is a valve, this is a valve, this is our directional control valve. So what you got to do is they draw this thing in its static or power off position. And what you got to visualize in your head is this whole thing. If I energize the solenoid, then that whole valve is doing what? So this is what you got to see. This is what you got to see in your mind is that it. So this is two solenoids. So we not only use the solenoid to shift it to the right, we use the solenoid to shift it to the left. And so this will be drawn in its at rest position. And then what you got to do in your head is, so right now, this is pressure. So right now the fluid would be flowing. It's going to go out this way. It's going to bypass this. So this is what we call a check valve. And you can actually see when the pressure does what, it unseats the ball. And what happens is it goes through here. It hits this. Pressure pushes it back. Right? Now we got all the fluid in here. It's got to go somewhere. So now what we're doing is we're running it through what we call a flow control valve. This is what we control the speed with. If you control it on the output, on the exhaust side, we refer to that as meter out. Pneumatics, hydraulics, it don't make any difference. Pneumatics, we need to meter out. Because what happens if you meter in, as soon as it moves, the air uncompresses, and then it's got to recompress. So what we're doing is we're pushing against something like this. And what happens is we meter out on pneumatics, we get a lot smoother motion. If we metered in, then what would it do? It would jerk. Hydraulics, it don't care. So we're running it through the flow control valve. This means it's what? Anybody know what, anytime you see that on any device, what does that mean? It's adjustment. So we can literally adjust the speed of the retraction, but we can also adjust the speed of extension. So we can control which one we want to, or we control the thing. Then it comes back here, flows out, goes over here, and goes down through the exhaust port. So we got to exhaust the air. Now what's nice, this is another big advantage of pneumatics, which is creating pressure with a gas, and hydraulics, which is with a fluid, is that 99.9% this is going to be air. So what can we do when we get through with it? Just send it back out. Yeah, and this, so we don't have to bring it all the way back to a tank. And then plus, we use lower pressures, so the piping does not have to be near what it is if you ever got into hydraulics. If you ever got into hydraulics, the piping is really, really metal. It's all metal, or high pressure too. Kind of like you got on your air conditioner out in your car. If you ever bust one of those, you better be prepared, because you can't fix them, and they're not cheap because they're high pressure too. So what happens? So let me erase all this. So what happens is we energize the other solenoid, and this is what you got to picture in your head. You got to picture what? The whole thing doing what? Shifting. It's not going to shift on the diagram, but that's what you got to picture. And this is, I did that by the way. It took me a long time to get the things lined up. So if I energize this solenoid, it shifts to the left. I energize this solenoid, it shifts to the right. It's going to be drawn in its power off condition. So that's the way the valve is going to be drawn. So now, if I do this, then now the flow comes up through here, goes up to this valve, bypasses the flow control valve, comes up through here, bypasses it, pushes the what? Pushes the actuator to the right. Where does the exhaust come? The exhaust it can't go through the check valve. It's got to go this way, back out to the exhaust. So we call this meter out. We do that with, we should do that with fluid power. I mean, not with fluid power. We should do that with pneumatics. A lot of times they'll do it with hydraulics just to set the system the same all the way through. We call this meter out. Meter out is when you meter the exhaust or the return to tank in hydraulics. Meter in is when you control the flow coming in. Normally with pneumatics, we meter out. Now this valve, it's got two positions. And it's got 4 ports. Now, the way they talk about these things, the ports are called ways, because that's different ways that the fluid can flow. So this would be a 2-position, 4-way valve, if you spelt it all the way out. But that's not the way the thing goes. So what they do is they start off with the number of ports, let's say a 4, the number of positions, 2, and then they say way, which is totally wrong, but that's the industry standard. So we'd call this a 4-2-way valve. And that's the way you'd order it. But it's 2 position, 4 ways. Notice the power and the exhaust are always what? Odd numbers. And then the working ports are always even. Pretty good. A lot of the hydraulics, this is the way I've seen it on pneumatics. Some of the hydraulic valves, they'll be labeled PT, instead of 1 and 3, they'll label it P and T. So P would be pressure and 1 would be tank, and then the other one would be 4 and 2. But you'll see that done a lot. So this is basically, so these directional control valves and these solenoids, what we can do is we can shift the valve electrically, right, or electronically instead of manually. In fact, this used to be, you can get in some old earth moving equipment, and they'll have these big old controls on them where you're literally manually shifting that hydraulic pressure. Now you get into one of these new ones, what do you got? You got a little joystick out there, because they're using these solenoid control valves to control all that pressure, and that's usually hydraulic. So adding solenoids to these directional control valves has really helped us a lot. So that's what these symbols are. So these symbols, so this is a symbol of the valve. And this is the symbol of the solenoid. Should have a slash through it. Some of the Festos don't do that. This would be a double solenoid valve. So this one, we're going to shift the valve, and something else has got to bring it back, right? You understand that? It's usually a spring, could be gravity. If you got a hydraulic jack for your car, it's a single acting cylinder. And what does it do? What brings it down? You have to use the weight of the car and the weight of the jack. So this is a symbol of the solenoids. So up here on the diagram, we don't see oh, this is the electric. This is a normally open momentary contact push button. This is a mushroom head push button with an indent. So this is our E-stop buttons. Festo line does not have E-stop buttons on it. The Amtro line does. And they're connected, so if you hit one of them, it kicks out the whole line. And you see can y'all see the mushroom head back there on the Amtro line, the big red ones in the yellow circle? Where are they located at? Right on the front. How many times you think I've leaned against the thing and kicked it? A lot. So somebody's gonna do that. I'll probably do it instead. A lot. You'll be sitting there talking and you'll kind of hit it. And it's indented, so you have to pull them out and then reset everything. A lot of your E-stop buttons actually grab, and you literally have to push them back in and turn them to pull them out. So you really got to know that. Here, we have an E-stop relay, so just because you pull it out, you still have to re-energize the system to do that, and we'll show you. These are relay coils. So the difference between a solenoid and a relay coil is the solenoid is supposed to have the slash through it and the relay coil doesn't. And I don't think we got I can't, trying to remember if we got any electrical solenoids back there. So these are the symbols in this class, Otis, that we need to know, right? Because once we learn that, we can come up here and look at this. And let me switch over real quick to, this didn't come in over here. So here's our PLCs. These are, we're using, on the Amtro line, we have 314 S7314C PLC. And what that does, it's a 300 PLC, but it's got a 304 CPU in it, which is the processor. It's got 24 inputs, and it runs in groups of 8. And in digital, we refer to that as bytes. So the way we address these things is if it's an input, we start off with I. Then I put the byte number. So this is byte 0 right here. 0, huh? No. That's byte 0. This is byte 1. So byte, if you hadn't had digital yet, or byte or even intro to PLC, this is a term that we use for groups of 8 bits. So Siemens PLCs, if you had Allen Bradley PLCs, they run in groups of 16, or what we call words. Siemens runs in groups of 8. So it's got 3 bytes, and this over here would be byte 2. Now, why do you need to know that? Well, the whole thing is wired up according to these. And when we look at the diagram, it'll make some sense. We have 16 outputs. And by the way, so this is going to be labeled input, here, input 0, bit 0. Bit is just a single digit. Yeah, and PLCs, well, PLCs, it depends on what you get. We call this guy a hybrid PLC, or I call it hybrid PLC. But it's basically a modular PLC, which means we can expand it. But what these newer a lot of these PLCs now, they'll have some internal input-output on them, and then you can add more if you want. So we still do have, I don't know what Siemens calls their true. We call them rack-mounted now. Rack-mounted modular PLCs. Allen Bradley does their control logic. It's still a rack-mounted PLC. What the advantage of a rack-mounted PLC is that the consumer gets exactly what they want. It's just like every computer that I've had at my house, except for one that I built myself because I got what exactly. And it's come by the way, desktop computers are really, really coming back in the gaming community, and I built a few of them already. One for my grandson and one for my soon-to-be son-in-law. Not son-in-law, it's married my granddaughter. I don't know what you call those. What do you call the husband of your granddaughter?
Son-in-law?
I don't know. So my oldest granddaughter is fixing to get married. Now on the outputs, so here they are. So when we look at the diagram, it's going to say, okay, this is hooked up. So let's go over here. Look. So here's this guy. So here's this push button right here. So we're running syncing inputs. So here's plus, and we'll show y'all how we can do it. So all this right here, here's the plus bus right here. So this is plus DC. And then this right here is the minus bus. Which, by the way, Germans color it blue. So here's the minus bus right here. We can change over, guys. And this comes up to a terminal board. So there's mine. So notice we're running syncing inputs on our PLC. That means all our push buttons and stuff has got to hook up to the positive. So notice here's this push button right here. Here's the start button. It's hooked up to the positive. And then the other side comes down. It's going to go to 0.0. So on our terminal boards, then 0, 1, and 2 are inputs, 4 and 5 are outputs. So that's the way they're labeled on terminal boards. And then this would come down into our PLC, and you can see it goes to input 0.0. And there's an LED there. That indicates that when I press that start button, you should see the LED on my PLC go true. So what I just did is I'm using my PLC, I'll check my push button to see if it's okay, then I'll check to see if it's getting all the way to the PLC. So those indicator lights on the front of that PLC is a extremely valuable troubleshooting. So notice all these go to input. So this is 0, 0, 0, 0, 0, 0, 0. These all go there. We'll get into it. So here we didn't have this. So here's the same thing. Here's sensors. These are 3-wire sensors. So 3-wire means they've got to connect to my plus. So the brown wires should go right there. And then they got to do what? They got to connect to my minus. So that powers them up. 4 is the normally open contact. It's going to be the black wire. So that black wire is running. I need to watch out for it. The black wire is running down 1.2. So 1, 2, and 3. 1, 2, 3. These are inputs. 4 and 5. Oh, here's a 6. We need to check that out. So it's coming down here to input 1.2. On my terminal board, it's going to be 1.2. But it's a 3-wire sensor. This is a magnetic sensor, but it's only got 2 wires. So this has got to be a reed switch. But it's still sourcing, right? And then, of course, this runs down. I'm not going to keep changing over. Input.5. And notice they give you the number right here. So to 3B, says I know it belongs to circuit number 3, right? I know it's a sensor. I know it's the second sensor in the circuit system. So what we're going to do, and what's nice about all these inputs, is that our front panel on our, and of course you're going to have to remember which one's input 0, which one's input 1, which one's input 2. And we can basically use your PLC to help us out a lot. That's 3 weeks. We only got an 8-week term. Only got an 8-week term. We've been 3 weeks. Got to have tests. So the review is out there. Anybody went and looked at the review? It is, but the problem is, James, you're okay. You mean, because you're always ready to graduate. We have some people that. They do, and they all do. And originally,
This one really does.
yeah. And this that when you take fluid power, you get to actually wire the circuits up. Or we're not gonna wire the circuits up, but we see how they work, right? Learning how to read these diagrams. This is very, 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 very important. And they're really set up neat where they, where they got you can actually look at them. The only problem, what's nice about the Festo line is that Festo label every sensor. They label every sensor, every actuator. There's a piece of that. What we have to depend on is so we've got the books that came on here. And so what we'll look at is we have these in binders up here, by the way. And it's got a picture of of each station. So we got a binder up here. And it's got a picture of each station, and it points out where the sensors are at. So you'll have to use that picture. You won't have to use it on the Festo line because I say if you look at the Festo line, they got everything labeled. And that might be a good idea, if you went to work and you had a label maker to go out there and label those sensors so, instead of trying to put a picture out. So, but odds are you're not going to see that, right? Odds are you're not going to see Festo. Odds are you're going to see wire numbers. You got to look at wire numbers or inputs. What inputs are they connected to outputs? Because that takes a lot of time to go out there. Our lines are small, but you go down to Mercedes and go through each one of those sections of their line and look at all the sensors and everything they have out there. And odds are they're the same thing you'll run into here. So,
Or you get to the part where I was at Crossoff, the company paid somebody to come out and redo all the machines because they were sitting out for 15 years. Well, they redid all the wires, didn't label a thing. So the original diagrams wouldn't help you because they stripped out all the old wires and redid the new ones.
that's usually in the contract. That's the way we used to write contracts, and all the mates. I told you about Dan. Was this class I told you about Dan? Dan Steele? What's the other class? About Dan redoing some lines out there, and then he retired. So Dan Steele was an engineer. He was a foreman, but he was an engineer at U.S. Steel, and they needed to redo some of the drives over the Finley. Well, Dan went over there and designed everything. We did everything. Didn't give U.S. Steel any of the documents. Dan retired. Then he became a consultant. And he was charging U.S. Steel like $100 an hour to come out there and fix what he designed because the engineers didn't want to get the documentation from him, even though legally they could have because he was working for them. So he was getting paid by U.S. Steel. So yeah, Dan.
That just sounds like ingenuity. It's their fault for being tricked.
Well, it's the people above him that should have got fired. But Dan made kill him. So he'd come out there. Yeah, I'll be right out. But when you work for anything, that's the responsibility of engineers. Is especially with a company like Mercedes, because Mercedes, there's no telling how many different companies came in to put that plant together. I mean, that's not one company that put that plant. They basically build modules. We were at EBC Engineering, and they had a robot module they were putting together for Mercedes down there. I think it was running an ABB robot, and they were putting it together. And then when they got all the programming, they're just going to move it down there. Well, the Mercedes engineers should want every piece of documents that come with it,
Anything in the robots now? They got, I think you contract with KUKA for the whole plant.
Not for the whole plant, because the paint shop runs ABB robots.
Right.
And then all the assembly robots are KUKA. And Whale, I think some of the Whale shop robots are different brands.
So
I think they got.
They don't pay. Mercedes, they don't have any Mercedes employees that do it. It's all contracted out.
That's contracted. Robots are contracted out. And that's what they'll do. A lot of the equipment, they pay a contract for. So, you gotta listen when people say they work at Mercedes or they work for Mercedes.
Mercedes.
there's a lot of people that work at Mercedes, but they don't work for Mercedes.
My aunt works for the place that hired me.
Yeah.
So she does all the tests.
So, and like I said, learning these prints, of course, is very, very important. And we got a book that's got the prints for each line. We'll look at trying to set up flow charts on the steps that it's supposed to go through and what's required to go through each step, and we'll look at those. In fact, that's a language you can actually program a PLC. That's a function block programming language where you can actually use those programs to see what's required to go between each step. So Siemens really like this, and we'll look at step charts too. So let me give this out. We need to do a last night. So the review's up there. It might have the stuff that's not on the